If we follow Figliola and Beasley and some others, we can formalize things a little bit more about our uncertainty by defining orders of uncertainty in a single measured quantity. Now, here's a system where we're using a TMP36 and a light sensor and a BMP180 to make some measurements. And let's focus in on the TMP36. We've used a capacitor here to try to reduce some of the noise that we're getting, but we're still getting some noisy data from our TMP36 measurement. And we'd like to know what the actual temperature is as a function of time. And we're measuring it with a resolution on our, in this case, an M0 feather board, so a higher resolution. Now, we're always going to assume a Gaussian normal distribution for our errors in this course. In other courses, we might look for something if we have evidence for another distribution, but we're going to stick with Gaussians in this course. And you'll get something close to it by combining multiple sources anyway. And remember, 95% of the variation in a Gaussian distribution will lie within plus or minus 2 standard deviations, this region in here, on a Gaussian distribution. And if you take many samples and average them, you're going to reduce the variation in the mean by the square root of the number of samples. So if I take 100 samples, my mean will have 10 times less noise in it than my single samples did. So remember, always base yourself on 95% probability, plus or minus 2 standard deviations, assume a Gaussian normal distribution, and watch out for people who talk about standard error when they're talking about uncertainty or talk about typical accuracies. They're probably just looking at 1 standard deviation. So you'll probably have to double those numbers. Now to start off with, we'll have a 0 order uncertainty. This is before we know anything at all about our measurement devices. And this is just plus or minus 1 unit of instrument resolution. So if our instrument is an analog to digital converter, we're going to go 1 step on the analog to digital converter. With our Arduino that has a 10-bit analog to digital converter and divides things into about 1,000 steps, that's going to be about 1 part in 1,000, which is not a very big uncertainty. If we've got a digital display, we'll use 1 step in the least significant digit of that digital display. Or if we've got an analog dial, we'll use half a gradation on that analog dial. If we've got something old-fashioned like a meter with a needle on it or a pressure gauge. This 0 order uncertainty is not enough to know what's going on. It's just a resolution measurement, but we can never have a better measurement than the resolution of our system. We can move up to a higher order uncertainty if we look also at the instrument uncertainty. And that's uncertainty due to noise and calibration issues or lack of calibration of our instruments. If our signal is constantly giving us different numbers just due to noise in the environment, then that's going to introduce some uncertainty. And we can usually approximate what that instrument uncertainty is going to be by looking at datasheet specifications. We can improve on those datasheet specifications if we calibrate our individual sensor using some more accurate standard sensor. And we can reduce the noise through averaging. So this instrument uncertainty, for a single measurement, we can take steps to mitigate it. At design stage, and we'll often talk about design stage uncertainty, we're planning to make a measurement. So this is before we've actually got any particular piece of hardware. So it's only going to be a first order estimate. If we want to get a higher order, second, third, fourth order estimate, we're going to have to consider more and more effects and measure more things about our measurement system. So our estimates at this stage need to come from the data sheets because we don't have any hardware yet. And we're going to have manufacturer's uncertainty in addition from those data sheets. We're going to combine the resolution and the instrument uncertainty by that root mean square formula that we've talked about before, we'll always use a 95% probability level and 2 standard deviations. And so our design stage uncertainty will be our 0 order uncertainty, that resolution uncertainty squared, plus this uncertainty associated with our transducer, this instrument uncertainty squared, then take the square root of both. Now, 2 Gaussians, just let's follow this along and see why we're taking this root mean square type approach. If we have 2 Gaussian distributions, we've done some simulations and we know that when we combine 2 Gaussian distributions to get a 3rd Gaussian distribution, we don't get one that's as wide as the 2 of them put together, that width plus that width. We only get a smaller width because of the fact that if we get a sample down here, it's probably going to be offset by a sample that's on the opposite side of this distribution. So this resulting distribution will be narrower than we expected. And that's what's accounted for by this root mean square summation of uncertainties. So a potential question we might ask is, what's the design stage uncertainty for a single temperature measurement made with a TMP36 transducer and recorded by an Arduino Uno? Well, we take the resolution of our Uno measurement and we would take the datasheet uncertainty of our TMP36 and we combine them with that square root of the sum of the squares formulation. Would it be lower if we planned to average over multiple measurements? Well, if we average over more and more measurements, the uncertainty, the variation in the mean, will go down as the square root of the number of measurements we make. But that's only for random errors. If we had a particular TMP36, then its manufacturing characteristics wouldn't change if we measured with it over and over again. So we would only get a lower uncertainty if we not only took multiple measurements from one TMP36, but took multiple TMP36s and measured the same system we were interested in with multiple different TMP36s with different manufacturing error biases. And if I wanted to ask that kind of a question, I'd probably have to feed you some critical information about what's going on with TMP36s and Unos. So the TMP36 is analog, so it doesn't have a resolution error. The Uno is a 10-bit analog to digital, so it's got 1,024 steps over the 1.1 volt range. So a little more than 1 millivolt steps. And the TMP36 sensitivity is 10 millivolts per degree C. So that 1 millivolt step would translate into a 0.1 degree Celsius uncertainty due to the resolution that we've got. So our 0 order or resolution uncertainty would be about 0.1 degrees Celsius. Now, if we had used, instead of the 1.1 volt range on the Uno, if we'd used the 5 volt range on the analog to digital conversion, we'd get a lower resolution and we'd have an uncertainty that was more like 0.5 degree Celsius due to our 5 volt range resolution. But now we go to the data sheet for the TMP36 for its accuracy, and we find this statement: do not require any external calibration to provide typical accuracies of plus or minus 1 degree Celsius at 25 degrees Celsius. Well, this says does not require any external calibration, so if we just pick a TMP36, we'll get a typical accuracy of about plus or minus 1 degree. This typical makes me think 1 standard deviation is 1 degree Celsius. And over the full range, plus or minus 2 degrees Celsius. The maximum error, which I got from this graph that was on the data sheet, looks like plus or minus 3 or even more degrees Celsius as we go up. So we're looking at a variation there that maximum makes me think this is 3 standard deviations, 99%. All the time we're going to be within that 3 degrees Celsius range. So the standard deviation, 3 standard deviations would be 3 degrees Celsius. So my estimate for the TMP36 instrument accuracy based on the data sheet is going to be about 2 degrees C at 95%. And this is largely a judgment call because they haven't really given me enough information here to tell me what the 95% uncertainty is. So I'm estimating here. And so if I wanted to say I'm going to take a TMP36, I'm going to plug it into an Uno, and I'd like to know at the design stage with no calibration, what sort of uncertainty do I expect? Well, my design stage uncertainty will be my resolution uncertainty plus my instrument uncertainty, both squared and then the square root. And if I take my 0.1 degrees Celsius for the resolution uncertainty and 2 degrees Celsius for the sensor uncertainty, the instrument uncertainty, take the square root, I'll still wind up with a value of about 2 degrees Celsius. So the resolution is having very little effect. The uncertainty is hugely dominated by the accuracy of the TMP36. And averaging won't change it because the noise isn't having any effect. It's all this instrument uncertainty. And if I've only picked out a single TMP36, then I don't have an average over multiple sensors that will allow me to improve my resolution or improve my measurement. Now, there's still some more noise out there. We measured noise in the temperature signal from a typical setup and found a standard deviation of around 0.14 degrees Celsius. And we don't know where that noise came from, but if we want to make a higher order estimate of our uncertainty, we need to include that noise into the uncertainty. So we take 2 standard deviations of that noise, 0.28 degrees Celsius, and combine that with our design stage that ignored the noise. And combining that, we still are only a little over 2 degrees Celsius for a single measurement. So the biggest source of uncertainty in a TMP36 measurement is the fact that there's a fair bit of manufacturing variation in the individual sensors that we could pick up off the shelf. And that's going to dominate our measurement accuracy unless we go and calibrate our TMP36. Easier than calibrating a TMP36 might be to get a better quality sensor that would allow us to have a better resolution straight right off the shelf. For this MCP9808 from Microchip, they've actually given us a distribution of temperature accuracies measured with actual units that they've selected off the shelf. And this is an averaging distribution taken over 854 units taken off the shelf and tested. And we see that very seldom do they get to much more than a quarter of a degree Celsius plus or minus. So they're claiming plus or minus 0.5 degrees Celsius maximum for their sensors. So typically 0.25 plus or minus 0.5 maximum. And what value would we use for uncertainty if we knew this information from the distributor, from the manufacturer of this chip? Well, we could use the maximum. We might be way over. We could use plus or minus 1, twice that maximum quoted number. Or we could use the 0.25, which they've said is typical. But let's look at the actual data we've got for the performance of actual sensors. I think, based on this one, that somewhere around plus or minus 0.2 covers about 95% of the measurements made with these transducers. So I'd say the uncertainty is around 0.2 degrees C based on their statistics. So that gives me an instrument uncertainty for this chip. I'd still have to go back to my resolution uncertainties to get a full design stage uncertainty for my measurements. So to recap, zero order uncertainty is all about instrument resolution. Instrument uncertainty comes from variations due to noise and calibration issues in the particular instrument. And the design stage uncertainty is a first order uncertainty. It's what we're going to get when we combine the instrument uncertainty here with the zero order resolution uncertainty there. And it's usually going to be a good enough estimate, at least at the time that we're selecting hardware, to know if our measurements are going to be accurate enough.